So this time we've got a satellite moving in an orbit around the radius of radius r with angular velocity omega, and so obviously it's going around the Earth and it's moving on the Earth's gravitational field. So assuming the force due to gravity varies inversely as the square of the distance from the centre of the Earth. So what does that mean? Basically, the force would be equal to k on r squared, okay, which we write as k on a squared, which with r is equal to a, and we'll get to that in a moment. But that's basically what it is. For the varies inversely will be k on r squared. It's not a term we use very often, but the force would be k on r squared there. That's where we get from varies inversely with the square of the distance from the centre of the Earth. So the radius is the distance there. Find an expression for r in terms of omega, a and g, where a is the radius of the Earth and g is the acceleration due to gravity. So when r is equal to a, the radius is equal to a, we get this situation. When r is equal to a, then the force is just gravity there. So at the surface, all we've got is is gravity. That's all that's acting. So gravity must be equal to k on a squared, or that constant k is equal to a squared g, and that's the key there, is to work out what it would be there. So when we get at a point P, which is above the Earth's surface, and it's moving at r there, so the force that's being pulled in there would be omega squared times r, or mass times omega squared times r, which would be equal to k on r squared. Okay. Now, we want to work out how far it is away from the Earth, so we want to write the expression of r, and I've used a little r. Really, I should be using a capital R in here. So really, ignore that that's a big R. It should be this R there. So it's equal to k on r squared, which means that the radius there be cubed and k on omega squared. Take the cube root, we get k on omega squared, or power of 1/3, or the cube root. And then the radius then would be, well, we know k was equal to a squared g, so we get the a squared g on omega squared and the cube root of all that. So that's rate value of the radius, or the expression for r in terms of omega a and gravity. This time we've got two rods, and they're at A and B and C, and they're both 0.5 of a metre, and they're smoothly jointed at B, so there's no friction, and the rod AB is jointly at A to a fixed smooth vertical rod, so there's our fixed smooth vertical rod. And the joint at B has a particle of mass 2 kilograms on it. We've got a small ring of mass 1 kilogram smoothly joined at B and C, and it can slide on the vertical rod below A. So basically, as it speeds up, that can move up there, so it changes the angle. So depending on what the velocity that it's moving around the circle in, because B will move around the circle, it depends on how high C would move up there. So the ring rests on the smooth ledge, root 3 on 2 below. So AC is root 3 on 2. AB and BC are both a half, so we've established that there. And it's going to move at 6 radians per second. So what we want to do is find the forces in the rods AB and BC. So we're at B, so we want to look at the forces there. There's a tension going in this rod, and there's a tension going in this rod. It's the way it's acting there. So there's going to be forces, and on forces on C then, there's going to be a tension force going back up the rod there. We forgot about saying that gravity's acting on the weight there at B, so a force of 2g twice gravity, and we've got normal forces opposing and going back up the rod there, and we've got, because it's the ring there, it's going to be mass times gravity, which is 1 times g. We've also got a normal force acting there. So there's the forces that are going to be there, and we know that the angular velocity, so omega is 6. So let's start solving those forces. So at B, towards the centre, we have 2 times omega, mass times omega squared r, And when we start to play with these ones, we know that in terms of that, that's stated there. So we're going to get forces in terms of T2 and T1 acting opposing mass times omega squared are there. So those two we're going to get is T2 cos theta and minus T1 cos theta. So that's going to be equal to, vertically we're going to have that. Sorry, I should have said that. So that would be T2 cos theta acting there. Okay, and we have T1 cos theta acting in the same direction as gravity. So that's why we can put those two together would be equal to T2 cos theta, but we've brought them all across to have it opposing to twice gravity. Horizontal, we said 2 omega squared r, and we have the 2 T2 sine theta and T1 sine theta, both acting that way. So that from T2, that would be T2 sine theta there, and this would be T1 sine theta, both acting opposing the mass times omega squared times r. So we know that omega is equal to 6, so we can able to put that in. We know the radius is square root of AB squared minus AO squared, which gives us a quarter. And we put, because they were both a half. We know cos theta would be equal to root 3 on 2, because we can draw our diagrams up, and sine theta would be equal to half, because we knew our values there. So we're able to sub all those in and get some equations. T2 minus T1 equals 4g on root 3, and T2 plus T1 is equal to 36. So to start finding our tensions, well, let's add the two equations. That will eliminate T1. And if we then do that, we get T2, or 2 lots of T2 would equal 4g root 3 plus 36, and then divided both by 2. And that would give us T2 is equal to 20 plus root 3, 20 on root 3, if we take gravity as 10, plus 18 newtons there. If we do a subtraction there of equation 4 minus equation 3, gives us 2 lots of T1 equal to the sum of these two, and then divide by 2 gives us the 18 minus 2g minus root 3 on root 3, and then taking gravity as 10, we get 18 minus 20 on root 3 newtons. So there's our two tensions in our string, in our rods. So at C, we get a resultant force of 0. So because the vertical components, we have m1 plus T1 cos theta is equal to 1g. So we know that T1 cos theta, we had T1 there. So we'll do our substitutions there, and we get N1. We can find N1 there. So there's our forces that we have in that part, because that's the force exerted on the ring there. So by the ledge on the ring. So what's pushing up against it? Okay, so that's because that's what we were seeing there, what was opposing the forces there. So there we go. So again, solving vertically, horizontally, doing a little bit more algebra. This involves a little bit more algebra to solve these ones, because we're starting to deal with more forces, because there's more rods and rings and components to this question. But that's what but if you solve all those forces at the different points, vertically and horizontally, you'll be able to get the tensions or the normal forces or whatever force we need to get in the problem.